Here we'll learn how to draw and interpret Davenport diagrams. To begin, start a table and denote some key principles of Davenport diagrams. Davenport diagrams are graphic displays of acid-base states. They illustrate the dynamic relationships between arterial blood pH, bicarbonate and non-bicarbonate buffers, and the partial pressure of carbon dioxide. An isopleth represents all possible combinations of bicarbonate and pH values at a given carbon dioxide partial pressure. Let's begin with a Davenport diagram of the four simple acid-base disorders prior to compensation. First, set up the basic graph parameters. The x-axis tracks pH. Indicate the healthy homeostatic arterial blood value of 7.4. Indicate that values less than this reflect acidosis, whereas values higher reflect alkalosis. The y-axis tracks bicarbonate concentration. Indicate the healthy homeostatic value of 24 millimolar. Recall that as bicarbonate concentration increases, pH becomes more alkaline. Next, draw the isopleth for a partial pressure of carbon dioxide of 40 millimeters of mercury. Then indicate the healthy homeostatic starting point where pH is 7.4. Bicarbonate concentration is 24, and the partial pressure of carbon dioxide is 40. Lastly, draw a straight line to represent the combination of all non-bicarbonate buffer titration curves. Now we're ready to show the uncompensated acid-base disorders in our graph. First, we'll show the disorders that cause the blood to become more acidic. Indicate metabolic acidosis occurs when the reduction in bicarbonate concentration lowers the pH. Notice that because this is a non-respiratory disorder, the PaCO2 is unaffected. Then show that because respiratory acidosis occurs when the lungs retain excess carbon dioxide, the partial pressure of carbon dioxide is elevated above normal, which lowers the pH. Recall that respiratory acidosis produces an elevated bicarbonate concentration, which is reflected in our graph. Now let's show the disorders that produce alkalotic, also referred to as basic states. Indicate that metabolic alkalosis occurs when bicarbonate concentration is elevated. As in metabolic acidosis, the PaCO2 remains on the 40 millimeters of mercury isopleth. Show that in respiratory alkalosis, the lungs release too much carbon dioxide, which in turn lowers the PaCO2 and increases pH. The lungs and kidneys respond to acid-base disorders via compensatory mechanisms that bring pH back to normal. Let's see what the arterial blood profile looks like when compensation is only partially complete. First, redraw the original graph and include the curves to show the 40 millimeters mercury isopleth and the non-bicarbonate buffer line. Then show that when metabolic acidosis triggers the release of carbon dioxide from the lungs, PaCO2 falls and pH increases. Thus, our point of interest lies lower and to the right than our original graph. Shade in the area that represents all possible outcomes of partial compensation for metabolic acidosis. The extent of the original disturbance and the magnitude of compensation determine the specific blood outcome. Likewise, show that when respiratory acidosis triggers increased renal excretion of hydrogen ions and conservation of bicarbonate, pH increases. The partial pressure of carbon dioxide remains elevated until the source of the disorder is treated because the lungs are unable to expel CO2. Then show that when metabolic alkalosis triggers respiratory and renal mechanisms to conserve hydrogen ions, pH lowers. However, because the respiratory component of compensation requires conservation of carbon dioxide, its partial pressure remains elevated. Similarly, when respiratory alkalosis triggers renal mechanisms that conserve hydrogen ions, pH lowers. But in this case, until the source of the disorder is treated, the partial pressure of carbon dioxide will remain below 40 millimeters of mercury. Now redraw the graph to show the outcomes when pH is returned to 7.4 by perfect compensation. As we'll see, the blood profile end states reflect both the original disorders and the compensatory mechanisms. If the original disorder was metabolic acidosis or respiratory alkalosis, both the bicarbonate concentration and the partial pressure of carbon dioxide are reduced, so-called isohydric hypocapnia. In the case of metabolic acidosis, this new state is accounted for by the cause of the disorder, which was a low concentration of bicarbonate relative to hydrogen ions, and the respiratory component of compensation, which required increased release of carbon dioxide. In the case of respiratory alkalosis, this new state is accounted for by the cause of the disorder, which was the excessive release of carbon dioxide, and renal compensatory mechanisms that excreted bicarbonate. If the original disorder was respiratory acidosis or metabolic alkalosis, both the bicarbonate concentration and the partial pressure of carbon dioxide are elevated. They're above normal. Isohydric hypercapnia. In the case of the respiratory acidosis, this is accounted for by the cause of the disorder, which was over-retention of carbon dioxide, and renal compensatory mechanisms that conserved bicarbonate. In the case of metabolic alkalosis, this was accounted for by the cause of the disorder, which was an increased bicarbonate to hydrogen ion ratio, and the respiratory component of compensation, which required increased carbon dioxide retention in the lungs. So finally, let's see what the Davenport diagram looks like in compound acid-base disturbances. First, show that if both metabolic and respiratory acidosis are in play, pH is reduced more so than if just one disorder was influencing pH. The shaded area shows the range of possible values that could result. Then show that when alkalosis results from both metabolic and respiratory origins, pH is elevated more so than if only one disorder was present. Be aware that while this information can tell us if there are one or two sources of the pH disturbance, it cannot tell us which preceded the other. This concludes our diagram.